Good. So now it's recording. I can share my screen. Goodness, it's not showing the. Let me close some files and see what happens. Okay, let me see if now it will show. It was not picking up. Yeah, now it is being picked up. So I will share my screen. Can you see the screen?
No. No.
Yes.
Okay, if you can't see the screen, maybe you can log in and log out again. Can you see the screen now?
Yes, we can see.
Yes.
Yes.
Good.
Yes.
Okay, so today we'll start on this topic of subgroups. We'll start with the definition. So if we have a group G and a non-empty set of the group, we call the group, the non-empty subset, we call it H. Then H will be a subgroup of G if H itself is a group under the same binary operation in G. Okay, so H is just a smaller group that is sitting inside another bigger group, but they have the same binary operation. We have seen examples of this already, and we shall list them shortly. So if H is it's a proper subset of G, then it is called a proper subgroup. That is, if H is not equal to G, it's strictly smaller than G in size, then H is called a proper subgroup. So the other notation that we shall be using is that if H is a subgroup of G, we can use this as a shorthand. So H, this less than sign here is used to mean that H is a subgroup of G. So this is common in a number of books. This notation means H is a subgroup of G. So let's look at some examples of subgroups. So for any given group, G, the whole group G and the sets containing only the identity element are subgroups of G. There will be subgroups. You can check that. So these are the easiest examples of subgroups you can think of. The whole group G is a subgroup, and also the set containing just the identity element is a subgroup. It satisfies all the 4 properties of a group, because if you multiply the identity with itself, you get the identity. If you multiply the identity with itself three times, you can put your brackets on any 2 of them. So the associative property is satisfied. The identity itself is in the set, so the identity property element exists, then the identity is its own inverse. So every element, which is just this one element, has an inverse. And therefore, this set containing only the identity turns out to be a group, and therefore a subgroup, because it's a subset of the group. Are we together?
Yes, yeah.
Yes,
On
we're
that?
together.
Good. So the next is a set of examples we have already seen. We know that the set of integers. So maybe I hope you're familiar with these symbols. This Z simply means a set of integers, all the integers. This symbol here simply means a set of all rational numbers, right? So the set of integers is a subset of the set of rational numbers, right? But we know that the rational numbers form a group under addition, just the usual addition of rational numbers, or of real numbers rather. And here also we know the set of integers forms a group under the same binary operation of addition. Therefore, we can conclude that the integers will be a subgroup of the rationals. And the rationals, again, will be a subgroup of the real numbers, because the rational numbers is a subset of the set of real numbers. And also the real numbers will be a subgroup of the group of complex numbers under addition. Okay, so these are just, these already we have seen these examples. We didn't call them subgroups before, but now we can, because we have defined a subgroup. So the next one says if n is a natural number, then the set of all multiples of n is a subgroup of z. Binary operation here is addition. So we define this set nz to be the set of all multiples of n. So for instance, if you pick, you can have, so this means you can actually find you can generate an infinite number of subgroups for z, because any integer, any positive integer that you pick here will generate a subgroup. So for instance, if you pick all multiples of 2, that will form a subgroup rather. If you pick all multiples of 3, and so on, that is also a subgroup. And the multiples of any integer will form a subgroup of z under addition. Does that make sense? So in your own time, try to check that this set of multiples of n will form a group under addition. Because if it forms a group under addition, then it means it's a subgroup of z under addition. So in your own time, try this. Check that these multiples of n, all multiples of n, will form a group under addition. So multiples of n will simply be written in the form kn, where k is an integer. So for instance, multiples of 2 will be written as 2k, where k is an integer. Are we together up to that point? Okay, then the next one says the following. You can hear me? Hello?
Yes.
Yes.
Okay, that's good. So the next one says if d is a natural number and d is a factor of n, then it turns out that nz will be a subgroup of dz. So for example, 4z turns out to be a subgroup of 2z, because all multiples of 4 is a subset of all multiples of 2. This set, this set of multiples of 2 contains the multiples of 4 as well. And both of them are groups under addition, and therefore this set is a subgroup of this. This group will be a subgroup of this group. 4z will be a subgroup of 2z. Are we together up to that point? Hello? Good, thank you.
Yes.
Yes.
Thank you. Good. So here is a theorem we can use. So anytime you want to check if a subset is a subgroup, there are two options you have. One option is to, I think there are people trying to join. Let me just admit them, then we can continue. Yes, so as I was saying, anytime you want to check if a subset is a subgroup, then you have two options, because a subset a subgroup is supposed to be a group. So one way to do this is to check that the set H, the subset, satisfies all the four required properties for it to be a group. So that is a fairly laborious way of doing this. It is quite strenuous, but this theorem allows us to do it in fewer steps. So one way is to confirm that the set, once you confirm that the set is an empty, then you simply need to check that these two properties are satisfied. So that means the set will be closed under the same binary operation, and for any element in H, the inverse of that element will also be in H. So if you find a set, a subset of G, that a non-empty subset of G that satisfies these two properties, then it automatically becomes a subgroup. So that means anytime you're asked to check if a subset is a subgroup, you just need to check these two properties. You check that it is closed under the same binary operation, and any element in the subset has its inverse in the subset. Are we together? So to prove this,
Yes.
so to prove this, what you need to do is the following. You see it says if and only if. So the first thing you need to do is, first of all, assume that that H is a subgroup, and if it is a subgroup, then these two conditions must be satisfied. So the second, the converse of a proof would be to assume that the two conditions are satisfied, and if they are, then H will be a subgroup. So let's prove it now. So to prove it, we first of all suppose that H is a subgroup, and if it's a subgroup, then it is also a group, right? So it will satisfy these two properties by definition. It will be closed under the binary operation, and every element will also be, any element in the set H will also have its inverse in the set H. So here we have confirmed that if H is a subgroup, then these two conditions will be satisfied. So we now look at the converse. So the converse is supposed to assume that the two conditions are satisfied for some non-empty subset H of G. So for H to be a subgroup, we need to show that these two conditions, if satisfied, will guarantee that H is a group. So that means those two conditions imply the remaining two conditions to make H a group. So let's see how that works. So if you use we already have these two conditions. We assume they hold, right? When we are considering the converse. So when the converse, we assume it's an empty subset which satisfies these two conditions. So automatically, the first condition says the product of any two elements in H will be in H. And if these two conditions are satisfied, it means A and A inverse will be two elements in H. So their product must also be in H. But we know that their product will be equal to the identity. So the identity will also be in H because of using the two properties. So we have three properties checked. The closure has been checked. We have checked inverse, and we have confirmed that identity element is in the subset. So the only property remaining to make H a subgroup is the associative property, and that will be inherited because the binary operation is the same, and the elements in H are all picked from G, so they can't behave any different from the elements in G. So we have proved the converse, and that is if the two conditions 1 and 2 hold for an empty subset of G, then that subset is a subgroup. So the second bit is just to show that this non-empty subset is a group on its own. Any questions on that? Kuna maswali? Okay, let's continue. This is now another result that we can look at. We will not prove this. This is a consequence. You can actually show that this one also holds. Now, the other thing is if you have a subset, another way to check that's a subgroup is if any two elements A and B are in H, then A multiplied by the inverse of B should also be in H. So this is another way to show it. Sometimes this is a convenient, or sometimes we can use the theorem we have just put here. So this can be used as it is, or you can choose to use this corollary. Any of the two will work. So if you want to check it's a subgroup, you can confirm if the two conditions of closure and the inverse are satisfied, or you can combine both of them into one condition and you only check this one condition. Simply confirm that the subset is non-empty and pick any two elements in the subset and show that the product of the first element and the inverse of the second element, in this case A and B, will be in H. And that again is sufficient to show that it is a subgroup. So the two can be used interchangeably. You don't use both. You can pick this one or the first way to do it. So here is another one which says if you have a group and H is a non-empty finite subset, note the word finite, then H will be a subgroup if and only if H is closed under the same binary operation. So the key word here is finite. We have a group, we don't care what the group is, but the subset is a finite subset. So you can try to prove these two results in your own time. I have not done the proofs on the slides, but these two results are useful also when checking if a subset is a subgroup. So this last one only works for a non-empty finite subset. It has to be finite. So here is an example, or more examples of subgroups, and we want to apply the theorems that we have learned to prove that these are subgroups of the general linear group, degree n. So suppose we take G to be the general linear group, so that's a set of all invertible n by n matrices with the real entries. Now we have two sets. We'll start with H. H is a set of all matrices in G which satisfies this property. So A, this means A transpose. This superscript here, capital T, means the transpose of A. So if you multiply A by its transpose, you will get the identity matrix. So we are claiming that we're claiming that this set is a subgroup of a general linear group. We shall prove that shortly. So the next one is a second set. Again, it's a set of matrices whose determinant is equal to 1. We earlier on, I think we did earlier on show that this is a group. The set of matrices that have determinant equal to 1, I think we did in the earlier classes. We showed that it's a group, but it turns out to be a subset of the general linear group, and therefore is a subgroup. But we shall use the techniques in this section to prove this. So are we together so far?
Yeah.
Good. So we'll go to the proof. So we'll start by proving that. So this set of matrices are called orthogonal matrices. This is a set of orthogonal matrices. Matrices which satisfy this property, where the inverse of a matrix is its transpose. We call them orthogonal matrices. You must have learned this in SMA303, linear algebra 2. So let's look at the solution. So let's consider the first set of orthogonal matrices. So we need to check closure first, so that if we pick any two elements in the subset, their product should also be in the subset. So let's pick A and B from H. Since they are from H, they must satisfy this property. They are orthogonal. It means the transpose of A is the inverse of A, and the transpose of B will also be the inverse of B, because that's what matrices in H behave, how they behave. So now we pick two matrices from there. We want to multiply them, and we want to see if the product will also behave the same way. So if you multiply any two matrices from H, A, B, let's check what happens. If you multiply the product by the transpose of the product, then you can write this second expression in brackets here. You can write it as B transpose A transpose. The transpose of a product of two matrices is equal to the product of the transposes of the individual matrices in reverse order. You also probably learned this in linear algebra. So AB transpose is the same as B transpose A transpose, and that's what I've done in the next step. Just replaced it with. But I know that B transpose is the identity, so I can replace it with the identity, which leaves me with A transpose, because the identity does not change any matrix. It leaves every matrix intact, so we can just drop it. But I know again that A transpose is equal to the identity, because I picked A from H, and it must satisfy this property. So we have shown that the product of the two matrices is orthogonal, because if you multiply it by its transpose, you get the identity. So this set is closed. We can conclude that AB is in H as long as A and B are from H. So the next thing we need to check is the inverse. By the way the set is defined, these matrices, if A is in H, its inverse is just the transpose. So we can check if the inverse is also orthogonal. So to check if it's orthogonal, we multiply it by its transpose. The transpose of this transpose is this. So we multiply A transpose by its transpose. And we know that transpose of the transpose is just A, right? And since A is orthogonal, A transpose A will be equal to the identity. And in any case, we know that A transpose is just in this case, is the inverse of A. So A transpose is not always the inverse of a matrix unless that matrix is an orthogonal matrix. This is a special case where the transpose turns out to be the inverse. So now we have checked that the inverse is also orthogonal, because if you multiply it by its transpose, you get the identity element. So the inverse of any element in H is also in H. And therefore we can confidently conclude that H is a subgroup of the general linear group. Is that okay?
Yes.
Yeah.
Okay. Should I move faster?
No.
No, we are.
The pace is okay.
Okay. No, I thought you had started dozing now, so that I move faster.
Yeah,
Okay.
very active.
Let me move to the next. You know, we had two things to prove. So now the second set we're considering was a set of all matrices whose determinant is equal to 1. So clearly this set is not empty because the identity element is in this set K. The determinant of the identity matrix is 1. So this set is not empty. It has at least one element. So what we need to do is to prove closure again. If we pick any two matrices in the set, then they will both have determinant 1 by definition. That's how they. So we need to check that the product of the two matrices will also have determinant 1, and then that will prove closure. So let's check what happens to the determinant of the product of the two matrices. Using this formula, determinant of AB is the same as the determinant of A times determinant of B. But we know the determinant of A is 1, determinant of B is 1, so we can make that substitution to get 1 times 1, which is equal to 1. Even after all these years, 1 times 1 is still equal to 1. So, and therefore we have confirmed that the determinant of the product of two matrices from K will also be 1. And therefore, this product must be in K. And that proves closure. So we need to check that the inverse is also, for any matrix in K, the inverse will also be in K. To check that the inverse is in K, we need to find the determinant of the inverse and confirm that its determinant must be 1 as well, because any matrix in K must have determinant 1. So if you pick any matrix A in K, the determinant of its inverse is equal to 1 over determinant of A, right? This again is from linear algebra, which is equal to 1. So the determinant of the inverse of A is also equal to 1, and therefore the inverse of A is also in K. And therefore we can conclude that K is a subgroup of the general linear group of degree n. Any questions? So this means you have to recall some of your linear algebra. I think someone is trying to join. Let's admit them. So are we together so far? So like I told you, it is important, as much as you can see these items on the screen, it's good for you to have a piece of paper and a pen and try to work them out on your end. There are two benefits to that. One is you understand things better when you write them down. And two, if there are any mistakes, you will help me to spot them. Because when you compute it and your answer disagrees with mine, there's a chance I've made a mistake or you have made a mistake. So that way we have an interactive session. So are we together? We can move on to the next part. The next example says that let A and B be a subset of a group G. Then the intersection of A and B will also be a subgroup. So this is another way to construct subgroups. If you know some two subgroups, you can construct another subgroup using this example. The intersection of the two turns out to be a subgroup as well. So let's look at the solution. Now, since A and B are already, this statement is not correct. It should be let A and B be a subgroup, not a subset. So let A and B be subgroups. I don't know why I made a mistake here. So let A and B be subgroups of a group G. I will correct the slides. For now, make that observation and note it down. Let A and B be subgroups of G. Then their intersection will also be a subgroup. So since A and B are both subgroups, they both contain the identity element, and therefore the identity element will be in the intersection. And that means the intersection will not be empty. It will have at least one element, and that's the identity element. So if you pick any two elements in the intersection, both must, there should be a comma. Sorry, no, there's no comma. If we pick both two elements from the intersection, then the two elements must be in both sets. X and Y will be in A as well as in B. And since A is a subgroup, the product of any two elements in a subgroup will be in the subgroup. The same applies to B. The product of any two elements in B will also be in B. So it means the product of these two elements is in both A and B, and therefore is in the intersection of A and B. And we can conclude that X, Y, for any two elements in the intersection, their product will also be in the intersection. So the other thing is we need to check that if you pick any element, its inverse must also be in the intersection. And since A and B are both subgroups, if X is in the intersection, then the inverse of X must be in A, since A is a subgroup, and the inverse of X must also in B, since B is a subgroup as well. And for that reason, the inverse must also be in the intersection. So we have checked the two conditions that are required for this subset to be a subgroup. And we can therefore conclude that the intersection of two subgroups is also a subgroup of G in this case. Is that okay?
Yes.
Okay. So as a remark, we can show that we can make this claim that the union of two subgroups is not necessarily a subgroup. This may not always be true. I've not given any examples, but we can, maybe the next class we can try to give some examples. In the meantime, you can also try this yourself and confirm that the union of two subgroups is not necessarily a subgroup. So for instance, just to use an example here, we have these two subgroups. So if you get the union of these two subgroups, it will no longer be a subgroup of G. And we can prove that. But I think that's just the example. We'll give some concrete examples later. So take note of this. But if a subset A is contained in B, and both are subgroups, then their union will automatically be a subgroup. So if A and B are subgroups and A is contained in B, then their union will automatically be a subgroup. There's more we can say about this, but I'll leave it for a different setup. So in the previous class, we defined the center of a group as a kernel of a homomorphism, but we also noted that you can define this center independent of the homomorphism. We defined it as a kernel of the homomorphism. Let's just stick to this definition. So let G be a group, then the set defined like this is called the center of G. So it's a set of all elements in G which commute with all other elements in G. So the claim we make here is that the center of a group is a subgroup of G. So let's prove this. We know very well that the identity element will always be one of the elements in the center. So the center of a group will never be empty. It it will have at least one element. Then let's pick any two elements from the center. Since they are from the center, we know that they will commute with all other elements in G. So that means AX will be equal to XA for any element X in G, and also BX will be equal to XB for any element X in G. This is because both A and B are from the center. They must commute with any other element from G. So let's check what will happen to the product. We need to check if two elements are in the center. Will their product also be in the center? So how do we check if they're center? We check if they commute with any other element in G. So if you multiply the product AB by X, because of the associative property, I can put my brackets anywhere. And since B is in the center, I know that BX will be equal to XB. Again, I can shift my brackets anywhere because of the associative property. And since A is in the center, AX will be equal to XA. And I end up with this at the end. So basically, ABX is the same as XAB. And therefore, this product also commutes with all other elements in G. So the product of two elements in the center will give you another element in the center. So that's the first property we need to check if a subset is a subgroup. So the next thing is to check if the inverse of any element in the center will also be in the center. So again, we check by simply multiplying. We know that if A is in the center, we can write A inverse X as this. This is from a property for groups we did earlier. Hopefully you can follow that. Now we know that A is in the center. Since A is in the center, it will commute with any other element of G. X inverse is also an element of G because G is a group. So A must commute with it, and therefore X inverse A should be equal to AX inverse. So, but we can say the following: AX, this one here is equal to XA inverse, right? Please put off your microphone. Is someone yawning really loudly? Okay, so what was I saying? This expression here that we have can be simplified as follows to get XA inverse. So what have we shown? That A inverse X will be equal to XA inverse. So if an element A is in the center, we have shown that it will commute with any other element in the group G. That is, we have shown A inverse X is the same as XA inverse. So we have checked the two properties. For any element in the center, its inverse will also be in the center. And therefore, we can conclude that the center is a subgroup of G. So I think that's a good place to stop, unless you still want to continue.
Okay, I was just inquiring if you can go back to the theorem. Like, I just want to put it down.
So most of these are already in the handwritten notes I shared, the scanned ones that I shared. Which theorem?
Okay, Peter. Yeah, that one. Thank you.
Okay.
Huku Turkana ndio hakuna network.
Simuongee na Safaricom.
Ni ngumu, wamekataa kufika huko, wanaogopa.
Watafika tu. Ama waanzisha yako bana. Uanzishe yako.
Yangu ndio maana nataka unipe knowledge. Ama hii knowledge hizi nisaidia.
Hii ukikuwa nayo unaweza anzisha kampuni kama 10.
Wazi. Ndio maana imenibidi.